Imagine a computer that thinks like a brain, but also operates under the strange rules of quantum physics.
To grasp neuromorphic quantum computing, we first need to understand two distinct ideas: neuromorphic computing and quantum computing. Neuromorphic computing designs computers inspired by the brain. Instead of a traditional CPU and memory model, these chips use many tiny units mimicking neurons and synapses working in parallel. Neuromorphic chips aim to replicate this brain-like behavior, processing information in a massively parallel and energy-efficient way, often using spikes instead of continuous signals. Quantum computing, however, is modeled after quantum physics governing tiny particles like atoms and electrons. Its basic unit is a qubit, which can be 0, 1, or both simultaneously. Imagine a normal bit as a coin lying flat, heads or tails. A qubit is like a coin spinning in the air, simultaneously heads and tails until observed. So, what happens when we combine brain-inspired neuromorphic computing with the quantum powers of superposition and entanglement? This is the essence of neuromorphic quantum computing, building brain-like networks that run on quantum hardware. Instead of classical neurons, imagine a network of qubits or quantum elements interacting like neurons and synapses, evolving according to quantum physics. This could lead to new ways to represent and process complex patterns, offering potential speed-ups in learning and optimization tasks. In a simple mental picture, each neuron becomes a little quantum system, with connections encoded in quantum interactions. When the network runs, it explores a cloud of possible activity patterns simultaneously. When measured, this cloud collapses into an answer, like a classification or decision. This is still early research, but neuromorphic quantum computing could help with complex pattern recognition, identifying subtle signals in noisy data. Furthermore, it might enable new forms of AI that are more efficient, adaptable, or can learn from smaller datasets, moving beyond today's GPU-based AI. There's also the idea of using neuromorphic methods to monitor and control quantum computers themselves, correcting errors and stabilizing qubits. What exists today are small experimental systems in physics labs, demonstrating brain-like behaviors like associative memory. However, a large, programmable neuromorphic quantum computer you can buy or rent does not yet exist. This field is primarily a research frontier. Scientists are excited because nature itself seems to favor this style of computing, combining the brain's parallel networks with quantum mechanics. It offers new paths to scale intelligence without increasing power consumption, addressing the limits of today's traditional chips and energy-intensive AI training. To summarize, neuromorphic computing is about building brain-like computers, quantum computing uses quantum physics, and neuromorphic quantum computing combines both. The hope is that these machines could one day recognize patterns humans can't see, solve complex optimization problems more efficiently, and run AI systems with less energy. For now, it's an emerging area, full of promise, but still in the lab. It's a direction of research shaping how future computing might evolve. Over the next decade, we'll likely see more experiments and prototypes. If you're curious about the future of AI and computing, this is definitely a field to watch.